repeat what you asked?
Are you needing the eta and C for like the bullet 2 and bullet 3 under question 3?
Yes, for all three questions, I need N0 and I need C.
Okay, and then are you looking for like a recursion tree or like master method or something?
Up to you, however you want to solve it. We are going to talk about recursion trees and master methods today, but
Okay.
you should not need them, but essentially you can use whatever.
What do you mean by don't need them?
Oh, for 2 and 3. Yes, for 2 and 3, you might need master method or recursion tree. Yes. Good
Okay.
catch. Any other questions?
So for question 2, log to the power of 4, and the second one also seems to be log to the power of 4.
They are different. You need to go through the slides and tell me what the values are, but they are different.
Okay, but I mean, okay, the second one, is it correct to say log to the power of 4 of 4? Is that how I should?
Okay, so let me bring it up. And Taha, yes, those are log based too. So one other thing that I need to mention to you guys, whenever you see log and okay, before I answer Taha's question, who asked the question about log to the power of 4? Could you tell me your name? I didn't.
Yeah, that was me.
Name, Zoom. Could you tell me your name? Ah, cool. So Taha, whenever you see log, it always means log base 2. If I do not specify it separately, it is going to be log base 2. If I use ln, that is going to be the natural log, that is log base e. Now, Parvez, let me get to chapter 3.
Okay, if it could be found in the slides, then maybe I could look it up.
It can be found in the slides, and let me just show you. If I can find it somewhere. Oh, slide 51. Cool. Yes. So, Parvez, so if you go through slide number 49, you should be able to understand what the two things mean.
Okay, thank you.
Perfect. Any other questions? 1 week from, so the due date is 1 week from now. So that is going to be, let's see, 17th of September. Yep. Any other questions? Cool. Okay, so let's start with today's class. And do not notice my screen, just notice my... Yes, Ravya, I think the lecture videos were uploaded, but I think there might be some hiccup with the YouTube algo or something. I will check on them. I think I will upload them within this weekend. Don't worry about it. Okay. So if there are no other questions, one thing that I should mention to you guys, when you are going to submit this particular code, for this, I would require that you guys submit a PDF document of your solutions. So you can either type it up in Microsoft Word and then convert that to PDF, or you can also write up your solutions in LaTeX and then submit that as a PDF version. Later down the line, I will require that you guys submit in LaTeX PDF format, but I will show you guys how to do that later. If you can submit it now in LaTeX, but if you don't know how to, type it up in Word and then submit it in PDF. Okay.
Are you fine with just scanning a paper?
Nope, you need to submit a digital copy.
Yeah, I meant like scan, like handwrite it and then scan it and send it.
Because handwriting is sometimes difficult to understand, I would prefer that you type it up even in Word document, that is fine, and then you submit that.
Okay.
Thank you. Because sometimes handwriting is a bit difficult to understand what's going on. And since you all are graduate students, you need to learn both PDF formats and LaTeX. They are your friends. Okay. So let's start with our lecture. So last time we were talking about recurrence relations, and you already had a quiz about that. So recurrence relations have three main components. The first part is going to be how you are going to divide your subproblems. So for merge sort, it was essentially dividing the array into two halves and then sorting those two halves separately. So we had 2 times t of n by 2 complexity. And then we have the default complexity of how we are merging those two arrays, and that became theta of n. And then whatever complexity we have for the base case. Right, so that was our basic complexity analysis for recurrence relations. And for merge sort, it tended to be 2 times t of n by 2 plus theta of n. And for binary search, since we are not bothered with the other half, it basically became t of n by 2 plus theta of 1. Because there was no merging process, essentially we are just dividing the array into half again and again, and the combining complexity did not require any n complexity. We are just checking the middle element every time. So we had the combined complexity of theta 1, and then we had the divide complexity of t of n by 2. Okay, so that was merge sort, that was binary sort. Binary search. We also looked at insertion sort, where every time we are reducing the array complexity by 1. So that is why we had t of n minus 1. And then we are going to insert that particular element at a particular location. That meant that we need to shift all our elements to the right, and that had a complexity of n. So that is why we had our problem complexity of t of n minus 1. So that is our subproblem complexity, and then shifting all the elements to the right became theta of n. Okay. So any questions about the recurrence complexity of merge sort, binary search, or insertion sort? Cool. So we have this particular program. Let's see. Yes. We have this particular program that is to find the factorial of a particular number. If n equals to 1, we return 1. Otherwise, we return n times factorial of n minus 1. Can anybody tell me so this is a recurrence function, right? It's a recurring function because the function calls itself. Can someone tell me what is the time complexity in recurrence relations? What is the complexity function for this particular program? Is it t of n squared? Is it t of n log n? Or what is it? Nobody remembers? You can say, I don't remember. That is fine as well. We have a t of n factorial. We have a t of n. Remember that we are looking for a solution that looks something like this. Okay, let me bring up. So we have, remember one thing, always whenever we are trying to find out the recurrence relation of a particular thing, it is going to be t of n, then it is going to be t of whatever the subproblem size is, right? Plus of the basic complexity of doing something that we are doing without any other subpartitions. So f of n, that is the thing that we do after we have, when we are trying to combine all of those problems, plus of the base case. Right, so we have this particular thing. So exactly, Brian. So think about this particular thing. So we have T of n, and we are trying to find out the factorial of this particular number. So every time we are calling factorial by n minus 1. So what is the subproblem size whenever we are calling this function again? Is it n by 2? Is it n by 4? Or is it n minus 1? You guys can type out an answer. This is not graded. Whatever you type, that's fine. Or you can speak out an answer. So Brian, Indu, and Vamsi think that it is n minus 1. Does everyone agree? Why do you think it is n minus 1? What would have happened if for some weird reason I had the code as n times, let's say that it is n squared times factorial of n by 2. What is the recurrent time complexity of this line then? Each time you're calling it with n minus 1, yes. Is it n by 2 or is it n squared? Come on, everyone. I need you to type the answers for this thing. I just have 4 answers. There are how many students? 42 students. So come on, I need more answers. So for the question is, when I return, instead of this particular line, if I return n squared times factorial of n by 2, then what is the subproblem size? Is it n squared or is it n by 2? Yes, Brian, you're correct. I am going to ask you guys forcefully to answer. If you don't answer, I will include a class participation points for this. I am not. Exactly, it is going to be n by 2, right? Because every time I'm calling my recursive function, I'm calling it with half the size, right? So for this particular case, when we have factorial of n minus 1, our subproblem size is n minus 1. Then we have the base case where we are combining all the solutions. So when are we combining all our solutions? When we are doing n times whatever this factorial function returns. So this particular function without the recurrence relation is going to be a linear function, right? We are just multiplying something with some other thing. So this is a linear function. So we have f of 1, right? Or we can also say this is going to be theta of 1. And our base case is again going to be theta of 1 because we don't have any other checks there. We just check if n equals to 1 and base case is constant exactly. So we have t of n minus 1 plus theta of 1 plus theta of 1. That is the same thing as saying t of n minus 1 plus theta of 1, right? So the time complexity of factorial is going to be